So this course on engineering maths, calling it 261 in the department, we'll start with linear algebra as the first topic. To motivate this, first let's see why should we engineers be learning something which seemingly abstract, such as linear algebra. So more than often we encounter in engineering problems a system of linear equations which can be written in the form of matrices. So normally when you're looking at linear regression or fitting something using least squares, or when you're solving for numerical, so you are trying to get numerical solutions to PDEs, then we set it up like finite difference, finite volume, or finite element. We end up getting matrices, a system of linear equations that you need to solve. And then even when you have to process images using MATLAB or something, whatever you do, in the background you would be dealing with matrices. Now, when we are looking at continuum mechanics, fluid mechanics or solid mechanics, we are dealing with stresses and tractions which are conveniently dealt with if we know tensor algebra, which is sort of a part of linear algebra. So that way it is very sort of useful for engineers to know linear algebra in sufficient detail. In this course, what do we want to achieve? We want to understand the concept of vectors. Apparently, as you would learn in this course, it is not just a vector can maybe very different from what you've learned. For example, you have learned that the vector can be written as in this form x1, x2, x3, or in this form x1, x2, x3 in the row form or the column form. We will learn that it's very different actually. We'll also learn about, once we are done with the concept of vectors, we will also deal with, learn about linear dependence or independence, right? So when we deal with vector algebra, essentially what we can do with these quantities called vectors, the algebra of those the operations between vectors. For example, we'll learn about inner product spaces. We learn about linear mappings or transformations where you can map one vector space onto another vector space, or the same vector space onto the same vector space using we can define a mapping between the two same vector spaces. In this respect, we'll talk about the meaning of adjoint, or what is the transpose of a linear transformation. Then we'll look at inverses of these transformations and what do they mean. We'll learn about how to handle matrices, various decompositions. We'll look at LU decomposition, QR decompositions. They're very useful in numerical linear algebra. We'll learn about them. We'll learn about eigenspectrum, or eigenvalues and eigenvectors, what they mean. We learn about the concept of tensors, so that we can handle second order tensor, third order tensors, and tensor of any higher order in general, how to see them, how to take this notion of tensors and use it to your advantage in solving some problems, right? Then eventually, when we define vectors and tensors on a let's say on an Euclidean space, then you would like to see how they vary over on like a field. If you have defined it on a Euclidean space, you would want to see their gradients, how to look at the gradients of a vector, or for that matter, a tensor, second order tensor, like a matrix. How does it change its properties as you move in space? For example, when people talk about stress, you talk about the force that is body force that you get because of a distribution of stress is given by del dot sigma, right? So it's a gradient of sigma. So how to sort of do the calculus in a convenient fashion, we'll see. Now, to begin with, what we'll do is we'll stick to the notion that you have of vectors. We'll look at elementary concepts of vectors first of all. This, like in beginning in the school, when we are taught that the vectors are what? What are vectors? Vectors are entities that have magnitude and direction, right? This is not really an entirely correct thing. They are much more than this. But then this definition at least helps us in defining quantities of physical relevance. For example, how to see force, velocity, position, and displacement. These quantities can be conveniently defined by just this uh, particular definition. So, for example, if you look at if somebody is talking about velocity of wind, let's say in northeasterly monsoons are brought about by northeasterly winds, let's say, and then you say, okay, northeast winds at a speed of 8 meters per second, then you know exactly what he's talking about. If you're talking about winds blowing from northeast with a speed, with a magnitude of 8 meters per second. Similarly, when we draw force, these free body diagrams, we look at force balance on a body and then say, okay, the net forces that are acting, we account for them. And then, for example, in this, the picture that is there on the screen right now, let's say there's a body with a center of mass placed here, and you have two forces acting on it, F1 and F2. The net force then is given by something called uh, vector addition, right? This is a special kind of addition. That's why we call it vector addition. It's essentially nothing but, in this case, component by component addition of the force. Right? Geometrically, this same equation can be represented by taking F1 direction, taking F2 direction, and then computing geometrically the F net direction. You can geometrically also add them like this. So sometimes you can call it geometric addition. Now, if you have three vectors, let's say U, V, and W, and you want to add them up. So you want to compute this vector U plus V plus W, the net vector U plus V plus W. Then you can arrange geometrically, you can do it this way. Of course, you can do algebraically by doing component by component addition, but you can geometrically see this picture as you place the V vector at the head of the U vector and the W vector on the head of the V vector. So this picture gives you U plus V, and then you add W to it. So you place the tail of W on the head of U plus V, and then you get U plus V plus W. So this, the way we have gone about it, we have done U plus V first, then added to this vector, resultant vector, a W, right? It turns out because vectors follow some property of associativity, as it's called. So whether you do U plus V first, in the same order, of course, in this case, or you do V plus W first and then later add U to it, they are the same thing. So how to see that? Let's see. Geometrically, we can see this picture like this. Let's say what you do is you have, uh, of course, you can do it here as P plus W, and then you add U to it. Use a different color here. So this is V plus W, and this is U, and then you add them together to get U plus VW. So what we have done here is this, and what we did earlier using this is here, correct? And they're equivalent, as you can see. So they follow something called associativity, right? Now, they also have an interesting property of commutativity, right? So whether you add U plus V plus W or you do U plus W plus V, they're equivalent. So in this case, the same thing you can uh, uh, get by saying this is u vector. You add w to it, you get u plus w, and then you now have placed the v vector here, and then you get u plus, this is essentially u plus w plus v, which is same as u plus v plus w because it follows commutativity, right? Then there's some spatial vector is there, which is a zero vector. When you add the zero vector to any other vector, it leaves it unchanged, right? So u plus zero is going to be u, and zero plus u is also going to be u. Okay, as simple as that. Now, addition is simple, straightforward, but can we subtract the two vectors as well? So what would u minus v would look like, be like? Okay, so how to define subtraction? Addition comes naturally. Subtraction is nothing but addition of negated things, right? For example, you can see u minus v as u plus of minus v. So you have to define the spatial vector minus v based on v and add it to u. Okay. Geometrically, we can see this way. So you have the u vector, the v vector, you reverse the v vector in this direction, you get minus v vector, and then you add to get u minus v vector. Okay, this is one way of seeing it. What we can also see is instead of when we are adding, we were adding one vector to the head, the tail of one vector was touching the head of the previous vector, right? And then you say this is u, this is v, and then you are adding u plus to get u plus v. If you want to subtract, you join the tails. You say this is u, this is v, and then what you get here is you get u minus v. You can think of it like that, or v minus u. Now, how to get the direction? So suppose if you want to if you put the direction to this line segment in this way to get this vector, then you are essentially head and head. You get u minus v, right? Whereas the negative of that would be v minus u. So if I join the head here, if I draw the vector like this, where head of this vector, resultant vector is meeting the head of the v vector, then you're writing v minus u, right? So this is also straightforward, all elementary stuff, of course, right? Now we can add, we can subtract, but we can also scale the vectors, right? So you have a vector u, you have a scalar. There is some special quantity which we'll deal with in a bit. That with this beta, it becomes a vector beta times u. So you are stretching the magnitude of the vector by this scalar beta. These scalars, for now, you can think of them as some real numbers or complex numbers. Okay. So when you talk about real spaces, you have a scalar which is real. When you talk about complex spaces, then your scalar is a complex number. So same way, the way you would scale with beta, you can scale with alpha, and then you can have this. Once you have scaled it with alpha, then you can scale with beta. Whereas, and in this side, I'm showing that if you scale after scaling with beta, if you scale with alpha, you get something like beta times alpha times u, and it turns out it would be equal to alpha times beta times u because that scaling factor that you get is same. Okay, that's a property of these scalars that you have. And if you put together scaling and addition together, you get these interesting properties like which is essentially like distributivity. You can think of it like that. So if you add the two scalars and then scale it with that, it's like scaling the same vector by them individually and then adding them up. The result is going to be equivalent. Or you can add two vectors and then scale it with alpha and then which is going to be equivalent to scaling both vectors with alpha and then adding them up. Although it looks trivial, but there's a small subtle point there that when you think of addition, this addition that has happened in this with respect to the scalars. So it's not geometric addition. It is essentially addition of two fields, right? Like real numbers being added, normal algebraic arithmetic addition that you know of. Whereas this addition that you have is sort of a geometric addition. It's like component by component addition or it's a vector addition. So it's a different kind of addition. So this sets the relationships between scalar addition and vector addition in this form. So although it looks very trivial, but of course there are subtle points here that are dropping hints on the properties of vectors, right? So we'll take up an example to just wrap up this particular revision of very elementary way of looking at vectors. So the thing is that let's say we sketch a line, the dashed line that I've sketched, and I'm sort of having two vectors, the vector A and another vector, let's say B. Now what I'm doing is I'm scaling the vector B with alpha and then adding it to A. So what I get is essentially A plus alpha B. Now A plus alpha B, as I change the value of alpha from minus infinity to plus infinity, I get vectors which are pointing to points that are lying on a straight line, correct? So in terms, I've sort of parameterized the vectors that point to this, that have their heads or that are pointing to the on line by this parameter alpha as it goes from minus infinity to plus infinity, correct? Now, yeah, so we have seen that we can do addition, subtraction, scaling of vectors, but can we take two vectors and multiply them, right? Of course, I'm sure that you have heard about these special multiplications that have been defined for vector spaces. For example, cross product, right? So normally denoted as U cross V, right? Then you have inner product, which is when you take two vectors, you end up getting a scalar, right? It's called inner product. Or a dyadic product, which is essentially you take one vector and then you do a dyadic product with v vector, and then you get something which is like a second order tensor in this case if u and v are first order tensors, right? Or just vectors, right? So, you have three kinds of multiplications. First multiplication gives you takes two vectors, gives you a vector. Inner product takes two vectors and gives you a scalar. And then you have a dyadic product where you take two vectors and then you get a second order tensor, right? Now, as you will learn later, that these particular products are defined only for some spatial vector spaces only, spatial class of vectors for which you can define these set of things. Like cross products, it has to be 2D space or a 3D space, essentially 3D space. Then inner products can be defined on something called inner product spaces, right? So they can be defined only for some spatial vector spaces. As you will learn once the definition of vector spaces is clear, okay? The definition of what is vector spaces. Now, there are other operations that we know from arithmetics, like for example, square roots and cube roots. So one you would ask whether you can do compute square roots and cube roots of vectors or not. I mean, of course, one can come up with a definition of a certain way of doing square roots and cube roots. Then you would ask yourself two questions: whether it's sort of useful somewhere or meaningful, essentially. Or the second question that you would ask is, can you do these operations on in a very generic way on the entire set of vectors that belong to the same vector space, right? So the applicability of whatever operation that you define should be very generic to the entire vector space, because uh, the reason why we deal with these entities or algebraic quantities in this fashion is essentially because they are all grouped together. If you do something on one, then sort of you can do it on the other as well, right? They're defined for the entire class. Now, the concept of length of a vector, because we started this part saying that okay, a vector is something with the direction and magnitude. So we are definitely talking about magnitude as a sort of length of a vector, right? So this inner product spaces allows one to define these the length, magnitude. Essentially, you can take this as for now. I'm sure you guys know it, but like I just write it for the sake of completeness here. That U transpose U is essentially norm of U square, right? It's like or U dot U is norm of U square, right? And it is, as you guys know, that you can perform it this way, that you arrange U transpose. If it's a column vector, you can write it in the row form. That's the U transpose, and then you do a special kind of product, take a product between the two, which is u1 into u1 and plus u2 into u2 and so on. So you get this u dot u, right? And that's what gives you the concept of length. And concept of angle, as you would see in a bit, also comes from the concept of length or concept of this inner product. That also allows you to define angle between two vectors. Now, before we move further, we should definitely spend some time on the definition of a vector space, right? What is a more generic definition of vector space? Given a quantity, how can you sort of say that it forms a vector space? Okay, so essentially expanding on sort of this particular definition that we have mentioned here, particular way, right? This is your vector. Okay, so we're going to tell you at the end of this lecture, you would see that not just this, but then you can even matrices can form a vector space. So your vector could look like this. It's not a collection of vector, it's just itself a vector. It also forms a vector space. Okay, we'll learn this. Now, before defining a vector space, what we'll do is we'll define some more algebraic structures, as I will call it. Okay. Okay, these are algebraic structures that people have defined over time to formalize this part of the stream of mathematics, this particular stream of mathematics. Okay, we'll start by defining what is something called group. I'm sure some of you would remember from your 11th or 12th standard, I think it was taught first time, what is a group. So we'll keep it just to definitions, right, for these quantities like algebraic structures and all. Will not elaborate too much on them. Now, consider a set of, let's say, I will represent the set as a like this is I'm creating a set, okay, like a Venn diagram. And I say, okay, elements are placed in the Venn diagram somewhere, like there are these elements of the set, okay, x1, x2, x3, x4. These are all elements, okay, there are elements. Now, this G essentially is a set. It's the most basic algebraic structure that you can think of. So you can, like for example, on my table there is a box, there is a book, there is a phone, there is. So collectively, I can make a set of these things, right? So there's a set. There's the most basic algebraic structure that you can form, right, of different quantities put together in a box. Let's say, correct? Group, as we'll see, is more special kind of set, okay? And this speciality of group comes from that if what can you do if you take two elements and perform some operation between them, okay? So we define an operation between two elements. Let's say we call it addition for now. Okay, and this defined between any two. This is like any two. It's a binary operation that you're defining. Okay, between two elements of a set. And yes, for us, the set is G. Okay, so now once we perform this spatial addition, this operation, you get another element x, let's say, right? The way this addition is defined, you do get some another element x. So the resultant x, uh, if it is forming a group, should also be a part of the set. Okay, so this x should belong to the set. It should also be an element of the set G. Okay, if x1, x2 are belong to, for belong to, we use this symbol. So if x1, x2 belong to G, are elements of G, then x also should belong to G. Okay. Okay, the second property of this spatial operation is that you have, if you add x1 plus x2 and then add x3, then this is equivalent to adding x2, x3 first and then adding x1 to it, to the resultant. And these would result into the same element x, which is part of the set G. Okay. This property is called, as we had discussed previously, is called associativity, right? This previous property is called closure. It's closed within this operation. So there is no need to bring in additional elements to define this new element that you've obtained by performing an operation between element 1 and element 2 of the set G. So it satisfies this closure property. Then in this set, there is also a special element which will denote by, let's say, 0. Now, this special element has the property that when you add any vector to it, it leaves it unchanged. So if you perform an operation between this spatial element with itself, with some vector x1, you will get the x1 back. Okay, and this is going to be true for every element that you can pick from the set G. For every, this is how we denote for every x1 that belongs to the set G. Okay, so now uh, this spatial element is called the identity element. So existence of the identity element is a must for something to be defined as a group. Now this identity element also helps us define something called inverse element. Okay, so if you have an element x1, then you can define an inverse element, which we'll denote by minus x1. And when you add x1 to its inverse element, you get 0. That is essentially the identity element. Okay. So if some set with a binary operator, in this case we're using plus as a symbol, so this becomes group is normally written by the set G, comma the operator. This is how you'll write a group. If it satisfies these four properties that we have listed above, then you call it a group. Okay. If the operator satisfies another fifth property, given by x1 plus x2 is equal to x2 plus x1, then you call this, of course, is commutativity. So if it satisfies commutativity, then the group is given as another special name. It's called an abelian group, based on that mathematician Abel, who uh, contributed immensely to the group theory. So it's sort of called an abelian group. Okay, so if some set G with an operator plus satisfies these five properties, then you call it an abelian group. Now, okay, we have a set G and an operator plus. What if I define another binary operator? Let's say an additional operator we define and we call it, let's say we denote it by dot, just to indicate that it could be a multiplication. Okay. So we define this another operation, binary operation dot, such that if G and plus operator forms an abelian group, that's given. That's one of the conditions. And G with the binary operator dot satisfies the first three properties. Okay, but it doesn't have an inverse. Okay, so like for example, integers with multiplication. The identity element would be 1. If you take one integer, multiply it by 1, you will get the integer back. But let's say if you take 2 into 1, the inverse element would be half, which does not belong to integers. So clearly, with respect to multiplication, it doesn't have an inverse, right? So in a group which doesn't have the fourth property, it just satisfies the three property, we call it a semi group. Okay, it's not a complete group. It uh, doesn't have inverse. Okay. Okay, it doesn't have inverse. Fine. The third requirement, let's say, is between these two operations plus and dot, they satisfy distribution laws. Now, what I mean by distribution laws is, suppose that you're performing in binary operation plus between x2 and x3, and then you want to take to the binary operation with the resultant uh, of the type dot, okay, multiplication, let's say. Then you can also write it as you can multiply x1 and x2 and then add it to x1 and x3, and they are going to be equivalent operations. Okay, so this is called distributive property. Similarly, on the other hand, if you put it like in this form, you can sort of look at it this way. It's the same thing, right? If it satisfies these properties, we call a triple now, because now you have a set G, you have operation 1 plus, let's say, and addition, and then you have, let's say, multiplication operation. It could be any kind of a spatial multiplication also. So if you have these three quantities together satisfying the above properties, then you call it something special called a ring. Okay. At this point, I would like to mention mathematician of Indian origin in certain ways, but Canadian born and an American national and working in US. He got Fields Medal recently. Suggest that you search for what topic did he get Fields Medal. Manjula Bhargava. I'm sure you must have heard about him. And you would see this word ring written there. Okay, you would know immediately. Uh, Now, when you would sort of go back and see it, then you would know exactly what he has sort of, not exactly, but sort of the rough topic that he has worked on, for which he has got field medal, right? Now, moving on. We keep adding things to the list of requirements, and we will keep getting special um, algebraic structures. So ring is an algebraic structure, group is an algebraic structure, set is the most basic algebraic structure, right? So if the dot product is such that this next in line, if the dot product is such that x1 dot x2 is equal to x2 dot x1 for every element x1 and x2 that belongs to, I should write it here very clearly that for every x1, x2 belonging to G, if this is true, and this means this means that it's commutative, right? Commutative with respect to dot. Then you call G plus dot as a commutative ring. Okay? Another name. Uh, in addition to being a commutative ring, if you have A dot C is equal to B dot C, and it definitely means once you have that relation, you can say A equal to B in that case, then we call such a structure as integral domain. Okay. Now suppose we were dealing with matrices. So clearly A multiplied by C is equal to, it may be equal to B into C, but it may not necessarily mean that A is equal to B, right? So it will not form a commutative ring, clearly. Okay, it doesn't form a commutative ring itself, so it will not also form integral domain. Okay, but an example of integral domain would be set of irrational numbers of the form a plus b under root 2, where a and b are chosen from integers. In that case, you end up getting a commutative ring and an integral domain, okay, that you can check. Finally, integral domains such that if inverse exists, right? So we said that G with dot, there is no inverse, right? It forms a semigroup. Uh, it forms a semigroup. But if inverse exists, right? In that case, that integral domain that we've defined above would be called a field. And of course, you have to avoid sort of, you have to define that way that inverse is existing except for one spatial element, which is the zero element. Okay, which is the zero element, which is the identity element with respect to addition. Okay, so this is how normally you will define fields. For example, a set of real numbers. Okay, uh, real numbers with respect to normal addition and multiplication forms a field. Okay, what else? Complex numbers with respect to addition and multiplication also forms a field. So they are the examples of field, and that's most sort of widely used algebraic structure that you will see, especially when it comes to vector definition of a vector. Now, till now, we have not defined what a vector is. We have talked about all the different kinds of algebraic structure. Now, what we'll do is we'll get to definition of a vector space, right? Just to revise what we have learned till now. So we defined a group, okay? Then we defined a spatial abelian group, right? Then you defined these are with respect to two operations, binary operators. Then you said, okay, you'll add another operator to it. Then you called it a ring. Then you defined a special kind of a ring which has commutative behavior, commutative nature with respect to the dot product. So you call it commutative ring. Then you said you have a special property of A dot C equal to B dot C, implying A equal to B, so that the structure with respect to the triple, with respect to that, you call it as an integral domain. And if you allowed the binary operator dot to, if it allows the inverse to be defined as well, then you get the sort of a constrained algebraic structure, which is a field. Okay, so all the real numbers and complex numbers define sort of are fields. Okay, now to define a vector space more formally, you can sort of use this picture. Okay, what does a vector space need? Okay, the way you will go about it is you have a semigroup. Let's call it G. Then you form. We'll use two sort of things. We'll use two sets. Let's say we are starting with two quantities. A group G with respect to something. Okay, let's call it F for some reason. Okay, F with the binary operation plus, and there is another one which is V with respect to some other plus. Let's call it star. Okay, there are two sets. One set is F with respect to plus, and there is a binary operation plus. Then there is another set V with a spatial addition or a spatial binary operation called star. Let's call it, right? Now we know that the next thing, if we have satisfy certain properties, then it can form a group. Let's say F and plus form a group, and V and star also forms a group. Okay. Then we say, okay, F and plus forms an abelian group, and V and star they also form an abelian group. Okay. Now we bifurcate here. We say, okay, this abelian group, we'll keep it here for a bit. Okay, and F will say, okay, for F plus we'll define another operation dot and then define a ring with respect to this set f plus and dot. Then let's say we'll have a commutative ring. So f plus and dot forms a commutative ring. Okay. It also satisfies all the properties for an integral domain, and not just that, it satisfies the properties for it to be defined as a field. So f is a field. Okay, f is a field. Now here we have an abelian group V with respect to star. Let's say star is a special kind of binary operation. We can call it vector addition. Okay, that's how you can see it. All right. Now we define a special function f which relates this function, this algebraic structure, with this algebraic structure. Okay. This spatial function f is required to relate the two. And the way you can see this is we talked about scaling of a vector. You can think of this function like a scaling vector, a scaling function, right? So together we, and I will say star, okay, in sort of small subscript, I can write this way, and field with respect to plus and dot, and this special function together. Okay, these three things are required to define a vector space. Okay. More formally, I think you can see it like it should satisfy this function f that we have defined should satisfy the following properties, the scaling function that we talked about. And we have already seen these properties, we have demonstrated these properties in a certain way when we were looking at scaling of the vectors, that elementary discussion we had on that, right? So let's say we have this function f that we're defining. It takes one element from the field, okay? It takes one element from the vector space V, and it gives you an element of the vector space V that we talked about, the group that we talked about in the previous slide, right? So a vector space is a triple of a abelian group V, okay, a field F, and a spatial function F that we're going to list down the properties of in a bit, okay? So this function F now is essentially, you can call it a scalar multiplication, okay, or just a scaling function, okay? It is defined such that the function f, if it operates on an already scaled vector, then it is equivalent to multiplying, okay, the two field elements and then scaling that vector b. So you're going to get the same vector. Let's call it a u vector, for example. Okay, this operation is going to give you the same vector u. Satisfies this. The function satisfies this property. You can add two field elements, which are like normal scalar addition, and then scale the vector v. It's going to be same as scaling with one element first, and then right as addition. This is vector addition. Okay, the star is nothing but a vector addition, and then I scale it with mu and then add them up. It's going to be the same. Okay, if it's a vector space, it has to be same, right? That's how the function is defined for this triple. You can add two vectors. I'll call it just add, okay? Spatial operation star, we said. It could be a matrix addition, it could be a vector addition. So it could be different kinds of additions. And then you scale with lambda. It's going to be same as scaling with lambda the two vectors separately and then adding them up, right? If you choose the scalar as 1, the field element as 1, which is the identity element of the field with respect to dot operation, then you're going to leave the vector unchanged. So this leaves it unchanged. That means you're scaling with 1. It's as simple as that, right? In these definitions, the lambda and mu, they belong to the field, and u and v vectors that we have mentioned belong to the vector, the abelian group that we had defined previously. Okay. Now, since V forms an abelian group, so in addition to these four properties which define the nature of the scalar function, it also should satisfy the abelian group properties with respect to the spatial operation that we have talked about. We can think of it like vector addition. This operation is nothing but we can call it vector addition operation. Okay, so it satisfies all the five properties that we had talked about. U plus V, if U belongs to V, capital V, the vector space V, then and V also belongs to the vector space V, then U plus V will also belong to vector space V. Okay, this is associativity. U plus V plus W is same as U plus, and then adding it to V plus W. They're going to be same. If you add zero vector, and zero vector is a must for V to form an abelian group, so you will find that in any vector space you will have a zero vector. That's a necessity. By definition it should have it. Then if you have an inverse element, and they also have inverse elements, so if you add U to this element you get 0. And also satisfy, because in a abelian group it also satisfies the commutative property. U plus V is same as V plus W. So now together, if you put it together, the property is 1 to 4, and A to E, that means together if you say these are 9 properties, right? If you 9 conditions or 9 properties, together using these 9 conditions, of course you can add the conditions to define a field as well. So at least these 9 conditions, they would give you the definition of vector space. Okay. Now let's take up an example. Okay. So let's say a set of position vectors R cube. Okay, this is a very common example. Just what we talked about when we just were talking about how to write a force or something, which a vector which is magnitude and direction sort of things. They were all coming from this R cube, right? A Euclidean space kind of definition. Here the field is essentially a field of real numbers. So essentially it's all the real axis is what forms a field with respect to addition and multiplication, scalar addition, scalar multiplication, right? Now we take if you take two vectors and add them up, the resultant vector addition is also going to be belong to the 3D space, it is R cube space, right? It will also satisfy the associativity property clearly. X1 plus X2 plus X3 is going to be equal to X1 plus X2 plus X3. If you have a zero vector there, when you add it, get the same vector back, right? The zero vector is nothing but 0, 0, 0. That's a zero vector, right? When you add it to X1, 1, X1, 2, and X1, 3, what you get is essentially X1, X2, and X3 back, right? When you add, this is what you get, right? Okay. So that is there. Then there's an inverse element also. X1 plus minus X1 is 0. And X1 plus X2 is same as X2 plus X1, right? So these 5 properties gives you that X1 and this vector space, the elements of R cube are satisfying the properties of an abelian group. Now, if we sort of to define the function f, you say, okay, you're going to just scale a multiplication. So mu times x1, and you then scale it, you get lambda mu times x1. Of course, it does that. Lambda plus mu times x1 is same as lambda x1 plus mu times x1. Yes, it does that. Lambda times x1 plus x2 can be written in this form. Yes. And if you scale it with 1, you get the vector back. Yes. So together we see that R cube with the field as real numbers and scalar function defined in this fashion here, using these four properties together, or all of them are satisfied. So you call, say that R cube forms a vector space. Okay, and the general vector that you will write would be, let's say, would have three components: x1, x2, and x3. Right? That's how you'll write. Now we'll go to another interesting example. We say that a set of n cross n matrices also forms a vector space. Okay. So if you take a matrix A and add it to another n cross n matrix B, then the resultant addition, this is now in this case, although we're calling it a vector space, but just to relate it to what you already know, you'll call it matrix addition, right? So what we're doing is element by element addition. That's what we're doing. And we call this plus as an matrix addition, right? So it will also belong to n cross n. Yes, it will belong to. So it satisfies the closure property. If you take three matrices and say A plus B plus C is equal to A plus B plus C, yes, it is. If you have a zero matrix, right? So you have, let's say if it's n is 2, then you have this as the zero vector. You can write it like this if you want. Or you can write it like this if you want. Or if you want to denote it some way, you can sort of also say this is the zero matrix. Okay. Anyway, so it's a zero vector anyway for this particular vector space. There is, of course, there is an inverse element minus a. When you add a to minus a, you get your zero matrix of n cross n size. It also satisfies the commutative property. It doesn't matter in the order you will add two matrices. Of course, the way you multiply is different. That's a different definition. But you can add in any order and you'll get the same resultant and result of the addition, right? You can scale the matrix elements in this fashion and they will satisfy this property. Also, this property, lambda plus mu times a is going to be lambda a plus mu a, right? And if you add two matrices and then you scale, that would be like equivalent to scaling and adding, right? And if you choose a scalar as 1, then it will leave it unchanged, right? Now here clearly the field that we have used is real, okay? In this case, it's defined. We could have used a complex thing also, but then we'll be talking about the elements of A being complex. That's the only difference it will come in, right? Anyway, putting together what we have sort of, because it satisfies all the 9 properties that we had laid out. So this triple now, I'll denote the triple as A as the A n cross n. I'll write it as, this is a set of all the n cross n matrices that you can think of, with the plus as the matrix addition as the binary operation. Field of real numbers and scaling function f. Together, when you put them together, you get a vector space. So that's the definition of a vector space. So in this lecture, what we have learned is we have learned sort of a proper definition of some of the algebraic structures like group, ring, and we have went on to define what a field is, right? And at the end of it, putting them together, we define something called a vector space. Okay, and we also noted that now with this new definition of vector space, you not just the old vectors fall into this category, but you can also define, for example, in this case, what we showed was that n cross n matrices would also form a vector space, right? Uh, right. So in the next class, we'll talk about fine, you have a vector space, but then what can you do with these vector spaces? What do they allow? What does this algebraic structure of a triple uh, quantities like a abelian group, a field, and an f, what does it allow you to do? Okay, and how does it enable you to do what do you call various things? Okay, which are very useful. So next time we'll start with something called linear dependence and independence, and then we'll move on from there to uh, inner product spaces. Okay, so this would be all in lecture 1. Thank you.